Hi, you guys. Mrs. Valdivia here. So we're gonna go over some Chapter 6 chemical reactions. All right, let's get going. So we're on Chapter 6 chemical reactions. Now you'll see me use RXN a lot to represent the word reactions, mainly because it shorthands it and makes it a lot easier, faster to take our notes. All right, so let's go. Let's start into knowing what is a chemical equation and what a chemical equation is composed of. So we have chemical equations. Okay. And we have reactants. And reactants are our starting material, right? So let's see some different colors here, some variation. Reactants are considered our starting material, and they're also known as reagents. Okay, that word's not going to fit, so I'm going to write it over here. So known as reagents. Then we have our products. Okay, and that is the ending material. So we also call that as what is being produced, what was made. So let's do an example. So in my example, I'm going to have some calcium carbonate. And with this one, there's going to be a little bit of change in it. So this little triangle means change. Most of the times we use it in mathematics. The change in temperature, so delta T, change in energy, delta E. So delta usually means change, right? We're adding something to create that change. Usually it is heat that gets added. Right? So here's our equation. This right here is your reactant, and these are your products. Okay, this is what got produced. All right, so let's look into ratios. Ratios is what we compare the number of atoms in a molecule, right? So compares number of atoms in a molecule. So example with this one would be like H2O, and we could say we have 2 hydrogens and 1 oxygen. So we call this a 2-to-1 ratio. And as it compares the number in the molecule, it also compares the molecules in a reaction. So in the reaction as a whole. All right, so the example we have this one where it's comparing it into a molecule using water again as our example. I'm going to have hydrogen plus oxygen gives me water. Right? We have to make sure that the number of molecules actually match. So if I have 2 hydrogens and 2 hydrogens, that matches. But here I have 2 oxygens, and over here I only have 1 oxygen. So that means I am going to need to multiply this water molecule by 2 in order to get 2 oxygens. So now I have 2 oxygens, That matches. But now I also have 4 hydrogens. So this 2 distributes into the whole molecule. So you distribute the 2. So this is going to be like 2 times 2, which is going to be 4, and 2 times 1, which is going to be 2, right? So we have 4 hydrogens, but I only have 2 here. Quite simple. I'm going to multiply that by 2, and now my equation is balanced, and I can tell what are the ratios that I have. But before we do that, let's go ahead and break this down a little bit further. Okay, these right here, these little numbers that we see here, these are called subscripts. Okay, and it's the number of atoms in a molecule. Right? And these ones right here, these big ones, I'm going to use a different color for them. So these ones here in front of the molecule, these ones are called coefficients. So we have subscripts and coefficients, and they show the ratio in which the compound reacts, right? So it shows the ratio in which the compound reacts. Let's just write the word reacts. And some of us like to see other words like form. So reacts or forms, right? Okay. Now, let's go ahead and write this in some other words. I'm just going to write in other words. Other words. Side note. Okay. Two hydrogen gas molecules. See, you guys can't see this, so let me fix this. Oh, I hope to fix it. All right, this little camera thing's weird. I gotta figure it out. All right, so 2 hydrogen gas molecules are required to react with 1 oxygen gas molecule in order to yield 2 water molecules. Trying to get this so that you guys can see the notes, but it's a little bit tricky. All right, there we go. So 2 hydrogen gas molecules, remember the G stands for gas, are required to react with 1 oxygen gas molecule in order to produce 2 water molecules. Right? I'm going to go ahead and turn this, and then let's create a visual and then write these ratios down. All right. So we're saying 2 hydrogens. So this is going to be my diatomic hydrogen. Okay, and we need 2 of these to react. So plus my oxygen, and oxygen is a little bit bigger, and it's diatomic oxygen. I'm just going to put in, it sounds OX. They look like eyeballs. All right, so required to react with 2 oxygen molecules in order to yield 2 water molecules. So our water molecule is going to look like this. Hydrogen, 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 and some hydrogen. And that's my oxygen. I'm gonna do this because it just looks weird to me and I don't like it. All right. And as long as we know that this is oxygen and this is hydrogen, gas, oxygen, gas, and this is going to be my water molecule. All right, so hopefully that's a good little visual for you guys to see. But here are going to be my ratios that I could obtain from this. Okay. I know that my ratios is going to be 2 of the diatomic hydrogens to 1 of the diatomic oxygens. Or I could write this as 4 of my hydrogens to 2 of my oxygens. If it asks you for ratios and it only shows it as 4:2, okay, that is another way to see that right there. If it says what are the ratios of your diatomic, that would look like this. What are the ratios of your atoms? That would look like that. Okay. We could also see ratios between this and this and this, right? So what if I had my ratio of my 2 oxygens, 2 of my diatomic oxygens, to 2 of my waters? That's possible. I could also show that as 4 oxygens to 2 waters, right? H2Os. Those are the same ratios. These are equivalent. These are equivalent right there. If I wanted to represent the hydrogen molecules, I could say that I have 2 diatomic hydrogen molecules for every 2 water molecules. And you guys, I messed up. This is actually just 1. So this is going to be 2 right there. All right, caught my little error. And so it's 2 oxygens for every 2 waters. Okay, and that's 1 oxygen. Okay, and this equivalency would be 4 hydrogens for every 2 waters. As you guys can see, it's just ratios. It's writing down what you guys have. It's nothing really complicated or anything. Just count what you have and compare them to each other. All right, now let's go into the next one called balancing chemical equations. We already did a little bit of this, but we're going to go more into it. Balancing chemical equations. All right. So this one, we're going to go through an example, and I'm going to call this example my grilled cheese sandwich. Okay. Making a grilled cheese sandwich. All right. So in order to make the grilled cheese sandwich, we're going to need 2 slices of bread, and we're going to need 1 slice of cheese. For my 2 slices of bread, that's going to kind of represent like a diatomic molecule. So I'm going to label my bread as Br2. And for my 1 slice of cheese, I'm going to label it as CH, just CH for cheese. Okay, so in order to make my grilled cheese sandwich, then let's write this kind of like in a way we could see it. We're going to need 2 breads, right? 2 pieces of bread. And my breads are diatomic, that means they have to come together. They're going to come together, right? And my 1 piece of cheese. Okay, so 2 breads and my 1 piece of cheese. Okay, this is going to give me 1 grilled cheese sandwich composed of a BR2CH. Right, and we're going to get a grilled cheese sandwich. All right. So let's say I have 8 pieces of bread and unlimited amount of cheese. So let's make examples. I have 8 pieces of bread and unlimited cheese. How many grilled cheese can I make? Many. And I'm just going to do this. How many grilled cheese can be produced? Well, let's go ahead and create our little equation. We know that the bread's going to come in 2s. And we need to know how many pieces of cheese we got to use and how much of the grilled cheese sandwiches are we going to produce, right? Well, the problem says we have 8 pieces of bread and they come in 2s. So that's going to be 4 of those. And in order to use up all of this, right, I'm going to have to use 4 cheeses. And I'm going to be able to produce, well, how many grilled cheeses? 4. Forgot the 2 there. 4. Okay. So I could use this equation to produce it. Now let's say our equation came a little bit different, right? What if our equation, person doesn't want 2 pieces of bread? What if they only want 1 piece of bread and then they fold that grilled cheese in half, right? So how many BRCHs can be produced? So now we change the end product just slightly. This one was BR2CH and this one is BRCH. So using the same amount of quantities that we were given, we started with 8 pieces of bread plus, I don't know how many cheeses I need yet, and that is going to yield a certain amount of BRCH of my grilled cheese sandwiches. Well, let's figure out how many can we use. Remember, he wants, and you know what? Let's do something else. Let's say in this one, we have 8 slices of bread and we have 5 cheeses. All right. So we have 8 slices of bread and 5 cheeses. How many can we produce? No longer is it unlimited cheese. All right. Well, I could put a 5 here, but this is going to be a little bit weird. It's not going to match the equation, right? 1 piece of bread to 1 piece of cheese. And if it's just 1 on 1 on 1, well, if I have 5, actually, let's make it work. Here we go. I have a 5 there. How many grilled cheese? I could produce 5. But it doesn't match. Do you guys see that? It doesn't match. So we have leftovers. And in this leftover, we're going to have leftover bread. We're going to have 3 bread left over. So that's my remainder of 3 breads. Balancing equation is just making things work for you in the correct amount of way. Now this leftover bread right here, this is called our excess reagent because it was left over. We have more than enough for it, way more than enough. The one that limited the amount we can make in this problem was the cheese. So this was our limiting reagent or reactant, whichever one you want to call it. Okay, it limited the total amount of substance that we can actually make. All right, we're going to go ahead and do another problem. And in my example, I want you guys to balance the following equation. We're going to have some iron plus some oxygen, and that is going to produce some iron 2 oxide. Okay. Our goal is to balance this equation out, and one thing when we're balancing is we're not going, we do not change the subscripts. So do not change the subscripts. Do not do that. These are the subscripts. Remember, those don't change, because if you change those, you're going to actually change the molecule that you have, right? So let's go ahead and do something called a T chart. This is my little T chart. I divide the equation between reactants and products, and then I'm going to write down how much of everything I have. Okay, so how much of everything I have on both sides. So on my reactant side, I so far only have 1 iron and 2 oxygens. On my product side, I have 2 irons and I have 3 oxygens. I could tell right away that none of these match, so therefore this equation is not balanced, and we have to figure out how to balance it. One of the things you want to look at is what are the common products for 2 of them, right? So if I have 3 oxygens here and 2 there, well, these are the lowest possible numbers you can have, right? They're not divisible within each other. So I could take 3 times 2 and get 6. And so 6 is the lowest common product between them. How do I get to that then? Well, 2 times 3 is going to be 6. So I'm going to multiply this by 3, and that's going to give me 6. And I can multiply this by 2, and that's going to give me 6. Now, when I multiply this equation by 2, that means I'm going to add 2 coefficients. And I want you guys to remember that this is the same as the distributive property, and I'm actually multiplying everything in there by 2. So it's 2 times 3 gives me 6, but it's also going to be 2 times 2 of irons. And that is going to give me 4 irons now. Okay. Here, this one, we multiplied it by 3. So I have to figure out what can I multiply the 1 by to get 4. Quite simple. We're going to just multiply it by 4. Now I have 4 irons. Everything matches, and that's exactly what we want. All right, let's go ahead and do another one. This one's going to be balancing polyatomic ions. So balancing polyatomic, which means more than 1 atom, ions. All right, so our example is going to be the following. Nickel nitrate plus sodium hydroxide gives me nickel hydroxide plus sodium nitrate. Okay. So let's go ahead and balance this out. One of the things you guys want to look for, let's use this marker, is identify your polyatomic ions. That is the the group of ions that gets repeated on both sides. We want to identify those. So here's a nitrate group, and here is also another nitrate group. Okay. We also have a hydroxide group and a hydroxide group there. So now that we identified those, we're going to go ahead and balance them together as a group. Okay, they're going to be balanced together as a group. I actually want to show you guys. Actually, no, we'll do that afterwards. So let's go ahead and balance this. Create our T-chart. All right. And we're going to write our groups down. Here I have nickel, and I have a nitrate group, NO3. I'm going to keep that nitrate group together. I also have sodium and a hydroxide group. Okay. I'm going to repeat these on this side, just as I wrote in here, so that I could keep good track of them and not confuse myself when I'm comparing the ratios. Okay. All right, so I have those there. Now I'm going to write down how many of each I have. For nickel, I have one here. I'm going to put that in parentheses. And I also have one nickel on this side. I have two nitrates. The 2 is outside of the nitrate, so it belongs to the nitrate because it's the parentheses are right here. It's literally just for this one, not for the nickel. So I have 2 nitrates. I have 1 sodium and 1 hydroxide. Let's look at this side. I have 1 nitrate, 1 sodium, and 2 hydroxides. Right away, we can see that our nitrates and our hydroxides do not match, and we need those to match in order to proceed into our work. So I'm going to need 2 nitrates over here. Well, I could just multiply this by 2, and that's going to give me 2. Right? So if I were to put a 2 here, I now have 2 nitrates, but I'm also going to be multiplying this sodium by 2. So now I have 2 sodiums. Okay. All right, my nitrates match. I'm not going to worry about the sodium yet. I'm going to try to do my hydroxide next. I have 2 hydroxides here, but only 1 on this side. So I'm going to go ahead and multiply that by 2, and that's going to give me 2 hydroxides. It's also going to give me 2 sodiums. Let's compare everything we have. 2 hydroxides, check. 2 sodiums, check. 2 nitrates, check. 1 nickel and 1 nickel, check. So now on the remainder of these, I'm just going to put a number 1. You don't want to get into the habit of leaving those blank. Leaving them blank, it's like saying, I don't know what goes there, so I'm not going to put anything down. Even though we already know, and we usually assume it's a 1, or it's obvious it could be a 1, put a number 1 down, all right? For your sake, for all the homework that you do, make sure you have that 1 written down so that we know, as your instructors, that you actually knew how to balance it, okay? And leaving it blank will get marked wrong. Okay, let's go ahead now and show these nitrates in molecule form. So here I'm saying I have 1 nickel. Okay, so here is my nickel, Ni. Nickel has a +2 charge. In order to balance this nickel with nitrate, and here is my nitrate, nitrates have a -1 charge. So it's just a -1. So this -1 can balance out 1 +1. So we're going to need another negative, NO3 negative, to balance out this charge, right? So we're also balancing our charges. This here plus this one, which is going to be our 2 sodiums. So we're going to have 2 sodiums. This is my Na for sodium. And sodium have a +1 charge. Are going to combine with my hydroxide groups, my OH groups. Right? So these are combined with a hydroxide group. groups, OH, each with a -1 sign. By the way, I know I'm not putting them together, but there is attraction going on right here between these, right here. Okay, that is because these are ionic bonds, right? What we learned in chapter 5, the different types of bonds. This is an ionic bond: metal, non-metal, metal, non-metal. Okay, all right. This is going to yield some nickel, and there's only one nickel, +2 charge, and hydroxide. We're going to need 2 hydroxides to balance out the 1 nickel, okay, plus sodium. And in this case, we have 2 sodiums and 2 nitrates, right? Because we have 1 molecule of each. So this is sodium and sodium with my nitrate, NO3, NO3. These have a negative charge. Sodium has a positive charge. Okay. These are linked together here. Okay, they transfer. Remember, ionic bonds transfer electrons, so they're not sharing electrons. They're not completely attached together. They are attracted through the polarity differences between them, right? One's more positive and one's more negative, so they have a polarity difference. Okay. We're going to create a word equation, and then we're going to turn that word equation into an actual equation. Okay. Let's go ahead, and I'm going to turn the page on this one. So, create and balance the word equation. So we're going to create and balance this word equation. All right, here it is. Ethane combines with oxygen to yield carbon dioxide, gas, and water. Okay, so there's our equation. We're going to go ahead and create it. Okay, so ethane is C2H6. Okay, so we're going to have to learn those soon. Okay, so C2H6 is our ethane, right? It's going to combine with oxygen, so plus oxygen, to yield carbon dioxide, so CO2, plus water. Right. There's a couple things we're going to have to fix. If you guys remember, oxygen is diatomic. So that means it comes in twos, like that. Oxygen is a gas at room temperature, carbon dioxide is a gas, and H2O is a liquid. Ethane is going to be a gas. All right. So now that we have those down, we're going to go ahead now and balance them out. So let's create our T chart. Okay. Carbon, hydrogen, oxygen. Carbon, hydrogen, oxygen. Okay. We have 2 carbons, 6 hydrogens, and 2 oxygens. 1 carbon, 2 hydrogens, and we have 2 oxygens on this side, plus 1 more. All right. Oh my gosh, how are we going to balance this, right? It's just a little bit crazy. Don't you worry, okay? We got a lot of different tricks for balancing these combustion kind of reactions because this is a combustion reaction. You'll notice that you have 2 carbons here, but only 1 here. You're just gonna copy that down. So I'm gonna go ahead and multiply this by 2 to get my 2 carbons. Okay. Once I do that, I'm also multiplying my oxygen by 2. That's gonna give me 4 oxygens. No problem, right? I'm going to look at my hydrogens and balance those out. I have 6 hydrogens here, but only 2 there. So I'm going to need to multiply this by 3 to get 6. So I'm going to multiply this by 3. That gives me 6 hydrogens. And that also multiplies my 1 by 3. And that gives me 3 more oxygens on this side. Now I'm going to make sure everything gets balanced. You're already looking what I'm looking at, right? So we have 2 carbons, 2 carbons, 6 hydrogens, 6 hydrogens. However, we only have 2 oxygens on this side, and we have 4, 5, 6, 7 oxygens on that side. Well, what are we going to do? How are we going to fix this problem? Quite easy, quite easy. Let's see here. Okay, remember I have 4, 5, 6, 7 oxygens total. Okay, so I'm just gonna go ahead and put that number 7 right here, but we're not done. Okay, and right here I originally had that number. That's actually a number 1. Oops, almost put a 2 there, but I meant to write a 1. Okay. So we still need to fix this, and what's the way? All right, so some of you guys are really good with math, and some of you guys have done this with math already. Awesome, fine, and dandy. You're probably better at it than I am. All right, so quite simple. We're going to take this entire equation. We want to get rid of this 2 down here, so we're going to multiply it by 2. That's it. So now we're going to end up having 2 of those. This 2 goes away. We're going to have 4 of these and 6 of those, right? And I'm going to rewrite this as 2C2H6 gas plus 7 O2s. And that's going to give me, the 2 actually doesn't go away in your equation. You leave it there. It's just kind of like that for you guys to see it, what it does. So we're going to leave it at 7 O2s, and that's going to give me 2 CO2s plus 3 H2. Oh, sorry, that was 6. Ooh, copying down the wrong numbers. 4 CO2s because we multiplied it by 2, and 6 H2Os. Okay. And this is our balanced equation right here. Kind of cool little trick. It works every single time for combustion reactions. This trick works all the time. You got an odd number of oxygens, right? So this is for when you have an odd number of oxygens. You're just going to write that odd number here, and then you're going to multiply the entire equation by 2. That's it. This number stays, and the other ones get multiplied by 2, and it's going to work out just fine whenever you do it. We can go ahead and start calculating it and figure it out, see if it works or not, but it should be just fine. Let's see. We're going to have, let's just do it just in case, right? It's always good to double check our work. What if I messed up? All right, so we're going to have 4 carbons. 6 times 2 is 12 hydrogens. 7 times 2 is 14 oxygens. Let's look at this side. I'm going to have 4 carbons. 4 times 2 is 8 oxygens. Let's look at my hydrogen. 6 times 2 is 12 hydrogens. And I need these oxygens as well, which is 6, so 8 plus 6 is going to be 14 oxygens. Ta-da, ta-da, and ta-da. It matches. All right, so remember, it works every single time that you have a combustion reaction and an odd number of oxygens. So we had an odd number of oxygens, which was 7. Just put that number down in this spot and multiply the whole equation by 2, and do not change this number. This is the only thing that you don't multiply by 2. All right, so we already know the word aqueous. Aqueous means dissolved in water. But I want you guys to keep that in your mind because we're going to be classifying reactions. So let's go ahead and go classifying chemical reactions. All right. So in classifying chemical reactions, we have 6 main different types of chemical reactions. So the ones that we have are going to be decomposition, synthesis, single replacement, double replacement, combustion, and acid base. All right, so we have decomposition. And for decomposition, actually, I'll go over those things later. Decomposition, synthesis, single replacement, double replacement, combustion, and acid base. Right. So those are our main kind of equations that you're going to see over and over again whenever we start classifying chemical equations. And it's important to know how to classify them, how they react, because when you start creating your chemical equations and trying to solve what kind of products are getting produced, you're going to be able to identify it based on the type of chemical equation that you have. Right? So, a couple things. Synthesis is also known as combination. Combination. You're going to see single replacement as SR, double replacement as DR. Okay. And acid base, you might also see it as a neutralization equation. So acid base neutralization or just neutralization equation. Um, there is names that we give some of these, and as we go through them, I'm going to give you guys the little nicknames that we've created over the years. Someone else created, I got taught these, and they're kind of cool, and it helps you remember what does everything do, right? So let's go through our equations. And I'm actually going to go through synthesis first because I'm going to create a little story as I go through this. So synthesis. And a synthesis reaction is similar to our marriage. Okay. Two people meet, they fall in love, and they get married, right? And its synthesis or combination is going to look like this. You're going to have let me do this. A plus B is going to give you a B. So let's put some different colors. I'm going to make A's blue. And I'm going to make B's green. Okay, just like that. A quick little equation that goes with it is going to be hydrogen plus oxygen gives us H2O. Okay. This is a synthesis, combination, a marriage of two things finding each other and combining together. So we're going to say two or more compounds combined together. Right? Now, just as when things don't work out, sometimes when we combine together or when the elements combine together, the energies are off. The energies do not mesh, right? One's producing more energy, one's not producing enough energy, and they don't work out, right? They could be volatile relationships. And that leads us to a decomposition reaction. Decomposition reaction. And a decomposition reaction is also known as our divorce. Okay. Our divorce. And our divorce reaction is going to look like this. A, B is together, and then A, B separate. And you're going to get A and B like this. Okay. They're separated now. They're divorced. They do not want to be together. So one compound separates into two or more compounds. The example I'm going to give you guys on this one is going to be calcium carbonate. Okay. Solid. Breaks apart to gives us calcium oxide plus CO2, carbon dioxide. Okay. So one thing breaks apart to give you two things, two or more things. So one compound separates into two or more. Two or more molecules, pieces, whatever you guys want to call it. All right, so now let's go into the third reaction, number 3, single replacement. And single replacement here, our SR reaction, is called the home wrecker. Home wrecker. All right, so why do they get divorced? Well, people sometimes divorce because of money or whatever. So this home wrecker, just for entertainment purposes, is going to be like the other person. What? No way. I thought molecules always lived happily ever after. Well, if you are more electronegative, which we learned in our last chapter, right, you tend to attract electrons more to you. So if you have oxygen versus fluorine, and oxygen is combined with, I don't know, silicon, right? Let's just say oxygen's combined with silicon, and they're happily together, like la 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 la. And then fluorine shows up at the doorsteps, like knock knock, hey, what's up, right? And next thing you know, silicon's like, ooh, fluorine. Fluorine has a lot more to offer, and then silicon just goes and meets up with fluorine, right? And leaves oxygen all by him, tiny little self. Right. So single replacement reactions are basically a home wrecker comes and separates, causes the separation of that molecule. Right? And this is what that one looks like. So we have an A and we have our B plus the home wrecker. And let's give the home wrecker a little color here. A plus B plus C. And next thing you know, we're going to have something a little bit different. We're going to have C, B, and A all by its tiny little self. Sad face. All right. So I wrote this down in a specific order because they separate in a certain fashion. A right here is going to represent my cation, while B is representing my anion. So this is a cation anion reaction, okay, put together. C right here is going to be my my other compound coming in, right? And we're going to figure out, well, what could it be? Remember, I said A is a cation, and cations are positively charged. Positive. All right. So cations are positively charged. Anions are going to be negatively charged. So if you have a positive coming in and now bonding with that negative, okay, this is going to be a cation, and this one's going to be an anion, right? That's going to be the new group form, and that's how they separate. And you get to figure out, well, what came in and caused that separation. And just like a cation could come in and cause a separation, so can an anion. The anion could also do the same thing. So I can have an AB here together. And let's say, in this case, I'm just going to call it D, because I don't want to confuse you guys. So now we're going to have a different compound. So now B is going to be all by himself, and we're going to have A, D combined together plus B all in his lonely little self. All right, so A in this case is still represented by my cation, and B is still my anion. And since this is a cation, that means that D must be my anion, right? So we already know that this is going to be an anion, and it's going to be negatively charged. So it's going to have a negative charge. So that means it's way more electronegative. So this pole here is stronger than this pole there. Okay, so this is an anion. And what I mean about that is that this reaction at the bottom is more likely to cause a separation of single replacement than the top one, because it's an anion coming in, and anions are more electronegative. So note that anions are more electronegative than cations. So what does that mean? That means they're going to attract more electrons from other elements towards them. All right, so they're going to steal the electrons from other elements. Okay, now that we did that one. Oh, we need to do our example. Okay, so let's go ahead and do an example here. So the first one, let's do a cation example. I'm going to have zinc solid on its own plus copper sulfate. And that is going to produce, I don't know, actually, let's see, before I write everything down, what is it going to produce? Well, zinc is a metal, so it means it's a cation. Copper is also a metal, so it's also a cation. And sulfate is a polyatomic ion, and those normally have negative charges, so it's going to be an anion, right? So we have a cation coming in and trying to replace copper, which is the other cation in this reaction. Later, we're going to go over metals that actually allow replacements. Okay, there's like a little metal chart that's like, oh, this metal will replace this metal, but this metal won't replace it. For right now, you're just going to go ahead and do it. Okay. So zinc is going to come and replace copper out of the way. So now you're going to have zinc sulfate, because it's removing that copper, plus copper all by itself. And copper is going to be a solid, and my zinc sulfate is going to become aqueous. Okay? My copper sulfate was also aqueous. Okay? Aqueous, remember, means dissolve in water. All right, now let's look at another one. If I have ammonium chloride plus fluorine. All right, we just talked about fluorine. What is going to happen here? Well, let's see. We have ammonium and we have chlorine. We know that chlorine is an anion. We know that fluorine is an anion, right? That means ammonium is going to be our cation. And it's one of the few positive polyatomic ions that has a +1 charge to it. Okay, so fluorine, which is diatomic and comes in twos. Okay. You can't even see that 2 that good. So it comes in twos. Fluorine comes in twos. It's going to come and replace chlorine. It's going to replace chlorine. Fluorine is the most electronegative atom that there is. The most. It's a 4.0 out of a 4.0 scale, right? It's the smartest of the bunch, and everybody wants to hang out. So it's going to come and it's going to replace chlorine. So now we're going to have ammonium fluoride. Ammonium fluoride, with the F right here, plus chlorine all by itself. Now, chlorine is also a diatomic element, which means that it's going to come in twos and it's going to be a gas, right? Ammonium fluoride is going to be aqueous. Fluorine, gas on its own. Fluorine by itself is going to be a gas. Now, you realize by looking at this, it's not balanced. So that means we got to go an extra step, take some extra notches, right? 2 fluorines, 1 fluorine. So I'm going to put a 2 there. So now I have 2 fluorines, 2 fluorines. 2 chlorines, but only 1 here. So I'm going to go ahead and put a 2 there, 2 chlorines. 2 ammoniums, 2 ammoniums. Everything is balanced, so I'm just going to put a 1 in front of this fluorine and a 1 in front of that chlorine, and now it's completely balanced. All right, next equation is going to be the double replacement. Okay. Well, sometimes couples realize that they're just having a hard time, right? And they're into something called open relationships. So they go dancing and they're like, you know what? I'm better at dancing cumbia and you're better at dancing reggae. So let's go find different partners that could dance what we like, right? So for that moment in time at the dance club, they become swingers because they're swinging their partners around and they're going to get a different partner. And what is that going to look like? It's going to look like this. It's going to look like AB plus CD, okay. And that is going to do a double replacement. Now, double replacement, A, which is my cation, because cations always get written first, is going to combine with D, and C is going to combine with B. So we're going to get, I can't really see these, so I'm redoing that right there. We're going to get AD. So A and D are going to combine together, plus C and B. This is known as a double replacement reaction. So the DR or swingers reaction. And going through an example for that one, we're going to have It's a bad marker. Potassium chloride. All my pens are drying out here. Okay. Let's use something that works. Potassium chloride, aqueous, plus silver nitrate, aqueous, and that is going to produce, what is it going to produce? So before I continue, let's see how this is going to move about. All right, silver and potassium are both metals. Chlorine and nitrate are going to act a little bit different. Those nitrate's a polyatomic ion with a -1 charge, and chlorine is going to be is an anion as well with a -1 charge. So in this case, potassium is going to replace silver and combine with nitrate, and silver is going to replace potassium and combine with chlorine. So that's going to be our double replacement reaction. And I know you guys could see this on your screen, but I can't, so I'm just going to do that to make it more visible. We're going to get potassium nitrate, KNO3, plus silver chloride. Simple as that, nothing else to it. Silver chloride is going to be a solid, and potassium nitrate is going to be aqueous. If you want to ask, how do I know that? Well, there's something called solubility rules. We don't really deal with tons of solubility rules, but we do have to learn them, and we're going to learn them sooner than you think. All right, so we've created our compound, and let's go ahead and see how this is. So our A's, right, used to be combined with our B's, but now it moved around. Our A has now combined with a nitrate, the NO3. Okay. So it's combined with D. So now we have an AD. And then our chlorine combined with silver, which was our C. Right there. All right. Next equation is going to be combustion. Boom! Boom! So it's like our bomb. It's our explosion. It's our fire. Let's just write fire, fire. Okay, see if you guys could remember it that way. So combustion reactions, it's combusting, it's producing heat. All right, it's producing that heat value. So we saw some earlier. Let's look at a basic one. We're going to have CH4, which is our methane, plus oxygen gas. And see. And in this case, we're going to need an energy source, a heat source, a fuel source, something like that. In this case, like our spark. And it's going to produce CO2 gas plus H2O liquid. Now, what are these? These are our covalent examples. So CH4 is methane, and it's a covalent compound. It's not ionic, not producing those charges, nothing like that. So this methane, which is our carbon-hydrogen-based group, so carbon-hydrogen-based group is our fuel source, and it's carbon-hydrogen-based. Okay. Now, in order to catch something on fire and maintain it on fire, you're going to need oxygen, okay? You're going to always need this, always. So every time you have a combustion reaction, you're always going to have oxygen right there on that spot. It's not going to change, okay? And then you're going to always produce carbon dioxide and water, always produce same products. The only thing that's ever going to change is your fuel source, whether it's methane or ethane or propane or butane, any of those, ethylene, that's going to be your fuel source. It's going to change, which is only thing that it will change from here is how many of each. And then obviously the physical characteristic of when the reaction actually happens, as some of these covalent compounds react more vigorously than others, right? So you'll get more of a boom or more fire than you will with some other ones. Now that we did this one, there's also the metals, because we have seen metals react, okay? So an example is going to be my tin, solid metal, plus my oxygen gas, right? This is going to be combined with a heat spark of some sort, and we're going to create tin oxide. So this is also known as a metal oxide, okay? And it's an ionic compound. So this one was covalent, and this is going to be an ionic compound, metal plus our non-metal. Okay. This equation here, this combustion reaction of our metals, right? It's a combustion reaction and a synthesis, because you're taking an A plus a B and making an AB with them. So you have combustion and synthesis in this metal oxide. Picking either or would be just fine. However, if it says pick all that apply, you need to make sure that you're like, oh, it's combustion producing that metal oxide. You know it's combustion because it has that oxygen. You have a metal plus oxygen. Always oxygen. Okay, notice that you have it up here and you have it here, right? And you have an AB to produce an A plus a B to produce an AB, which gives you a synthesis reaction. All right, last but not least is going to be our neutralization acid-base reaction. Acid-base neutralization reaction. All right. So in this one, I'm going to have some hydrochloric acid. By the way, that shouldn't be capital. I accidentally capitalized that L. It should be lowercase. So if you do yours, make sure that you put lowercase. Do not capitalize it. So hydrochloric acid plus sodium hydroxide. And what's going to happen? Okay. So an acid-base reaction is similar to a double replacement reaction. Okay. What that means is that my positive hydrogen is going to take the place of that sodium, and it's going to combine with my hydroxide. This sodium is then going to combine with my chlorine. Okay, so we're going to get this kind of reaction. Right? Hydrogen with hydroxide, sodium with chlorine, and we are going to produce the following. We're going to have sodium chloride plus hydrogen hydroxide. Okay. Liquid, aqueous, and aqueous. You'll notice that the only one that's liquid is the HOH. What is HOH? There's 2 hydrogens and 1 oxygen, so HOH is actually water. Okay, so it's water. So here you're going to have sodium hydroxide, which is going to be table salt. That's the actual official name of sodium hydroxide, is a table salt. And this one is going to be our water. So in a neutralization reaction, you're going to have the following. You're going to have your acid plus your base. And our base is usually going to be this hydroxide group. and you're going to produce a salt. It doesn't have to be table salt. Remember, the official name of this is table salt. All in all together, it's just going to be a salt. You could have magnesium chloride, and that's going to be a salt. You're going to produce a salt plus water, which is going to make it neutral, okay? It's going to make it neutral. So acids have a pH less than 7. So it's between 0 to 6.9. A base has a pH greater than 7. And it's a pH of 8 through 14. Something is considered neutral if the pH is 7. So that means like 7.0 to 7.9. Okay? And that is considered neutral. All right, so that was the end of classifying chemical reactions. There is still, let's see, actually not that much more. All right, so we're going to talk about the dissociation. So a couple of key words here: dissociation, which is compounds separate into ions when dissolved in water, right? So dissociation means your compounds are separating into ions when dissolved in water. This creates our aqueous solution. So this creates aqueous solutions. Okay, let's go ahead and look at an example of hydrochloric acid in its aqueous state. All right, so I'm going to start with, I'm going to have a cup here, and then we're going to look at dissociation. What happens during dissociation? All right, so in this first one right here, I have some water, H2O, and I'm going to have some hydrochloric acid. So here is my water molecules. We know them because they look like little Mickey Mouses, right? And we're gonna have my hydrochloric acid. So that's gonna be this one here. Okay. And what I'm saying is this is what we think it looks like, but in reality, it's gonna dissociate because we have it mixed inside water, right? This is my H2O. So what we're going to get is something different. You're going to get some random hydrogens floating through and some random chlorines floating through. Now chlorines are a little bit bigger than our hydrogens. Okay. We had like 2 of those. And your water actually also dissociates inside of here. So you'll have some oxygens and some more hydrogens actually in it. Then let's just go ahead and draw the oxygens. Okay. And so we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Give them a couple more hydrogens. 5, 6, 4. All right. And let's label those so that we don't forget. This is my hydrogens with the positive charge. Okay. And these hydrogens came from my water molecules. And they came from the hydrogens connected to my hydrochloric acid. Okay. This little compound right here is my negative chlorine. Okay. So the ions are just now floating around. This is my negative oxygen. Okay. This is called dissociation right here, right? You had your hydrochloric acid, right? Aqueous, which means dissolved in water. And in its dissociation form, you're going to have hydrogen with a +1 charge plus your chlorine with a -1 charge. And this is aqueous. Remember, still dissolved in water. Um, a couple things to know is that hydrogen is a +1, if you guys remember that. So it is in group 1. So this is just reviewing our previous chapter. Because it's in group 1, it has one valence electron. Um, if it has one valence electrons, how many bonds can we make? We can make one bond. And it's in group 1, so how do we know the charge? Well, everything in group 1 is going to have a +1 charge. All right, let's go ahead and look at chlorine. Chlorine is in group 7A or 17. Its valence electrons is similar to the group that it's in, and that is going to be 7 valence electrons. The number of bonds it can make. Well, is it going to gain electrons or lose electrons? Remember, it wants to reach an octet, and it's going to take the easiest path possible. So the easiest path for it to reach an octet is to gain one electron, making it have one bond available. The charge it's going to have is a -1 charge. So the reactions that we see are going to be between metals and nonmetals mainly. So you're going to have a metal plus a nonmetal, which we know is an ionic compound. So this is ionic compound. And the reason we have that is because almost everything in our periodic table is a metal, and they're positively charged, and they're going to be attracted to the negatively charged atoms, which is going to make them ionic compounds. Okay. So an ionic compound is when you have a metal cation combined with a non-metal anion. So this is going to be a cation, a metal cation combined with a non-metal anion. Let's go ahead and take a look at one of those reactions. Sodium metal plus chlorine gives me sodium chloride. Okay. Something quite simple. It's going to be producing that table salt. The first thing we want to do is we're going to give it a quick little balance. Chlorine is diatomic, so it comes in twos. They have a 1 here, so I'm going to put a 2. 2 chlorines, 2 chlorines, 2 sodiums, boom, throw there, 2 sodiums, and now just put a 1 there, and it is completely balanced. Okay. So what does this mean in dissociation and figuring out charges and whatnot? Well, let's see. We want to figure out the charges. Like, we want to figure out the formal charges of all of our compounds in this one. Make sure everything is correct. And then from figuring out the formal charges, we're going to figure out the oxidation state. All right. When you have a solid or a gas by itself, its oxidation number, because it's by itself, it's not ionized, is going to be 0. Okay, it's by itself, it is not ionized. However, you have sodium and chlorine here, but they're combined together. And we just said on the last one that depending on what group they're in is the charge they make. Sodium is in group 1, so it's going to make a +1 charge. Chlorine is in group 7A, so it's going to make a -1 charge. It's a 1. Right? If you combine these together, you're going to get a net charge of 0 for this molecule. However, this is what we have up here. And like I said, we're going to use that to figure out the oxidation states. All right? And what that means is we want to know if something is oxidized or if it's reduced. Like, what? Well, let's go over those keywords then. Figure out what is what. So oxidized means we want to know what lost electrons. So it lost electrons. Reduced means it gained electrons. Right? So in order to find that out, we're going to do half reactions. Half reactions. So the half reaction starting with sodium. Sodium went from a 0 charge to a +1 charge. If you become more positive, did you gain or did you lose electrons? Well, if you become more positive, right, you lost negative electrons. So in this case, we lost, right, lost electrons. And we're going to make the half reaction of chlorine. And in that half reaction, we can see it goes from a 0 to a -1. If you become more negative, right, that means you've gained more negative electrons. So you've gained electrons. So what does that tell us? That tells us a couple things. That tells us that sodium lost electrons, and if you lose electrons, you are oxidized. And chlorine gained electrons, so chlorine was reduced. Okay, chlorine was reduced. And the best way that I could actually help you guys remember this is Leo's grr. Leo's do what? Leo's grr. All right. Okay, so Leo's grr. Lose electrons. Leo, lose electrons. You are oxidized. Because the Leo goes grr, right? It oxidized. But if you gain electrons, right, you're more negative. Nobody likes no negative people. You are reduced by your negativity. All right. So Leo says GER. Lose electrons oxidized, gain electrons reduced. Let's write that down. Lose electrons, you're oxidized. Gain electrons, you are reduced. All right, so if it starts asking you for oxidation states or redox, this is also known as redox reactions, then you're going to have to figure out your half reaction, right? And that is by figuring out, well, what are the oxidation states of each individually? If you have a solid by itself, it's an oxidation state of 0. A gas by itself, it's an oxidation state of 0, right? But if you have something that's aqueous, that means it's ionized, right? And we know it's ionized because we just learned about dissociation and things break apart into its ionic form. Okay? The other thing that's going to give you a 0 oxidation state is going to be a pure liquid. So a pure liquid is also going to be a 0 oxidation state. All right, you guys, that is it. Let's see, I think. Oh, no, one more thing. Whew, I thought it was going to be it. You guys were like, finally. So was I, trust me. But no, one more thing. And then we can move on. Because if we don't do this, chapter 14 is going to be a total chaos for you guys. All right, so reactions in aqueous solutions. Reactions in aqueous solutions. Okay. Whew. Right? I almost messed up there and didn't give you this. All right, we can show 3 ways in which reactions occur. All right. Well, more than 3 ways, but the main 3 that we like to see are molecular, complete ionic, and net ionic equations. So far, we've been looking at molecular equations, and we're going to break those up into our complete ionic and our net ionic equations. So let's go first into molecular. So we write equations, that's equations for neutral compounds. And when we write the equations for the neutral compounds, we want to make sure we're using phase changes, solid, liquid, gas, aqueous, those kind of things. So we want to use phase changes or the symbols. I should have wrote symbols. No, actually, I'll still write it. We want to use the symbols to indicate what state they're in. So phase change symbols. And that's going to be solid, liquid, gas, aqueous, dot, dot, dot. So let's go through an example. Lead nitrate, aqueous, plus 2 potassium chlorides. I'm going to go ahead and balance this out. We'll produce double replacement reaction. I hope you guys know this. You have 1, 2, AB plus CD. We're going to get lead chloride plus potassium nitrate. All right. So it's going to be one of these, 2 of those. So 1 lead, 1 lead. 2 nitrates, 2 nitrates. 2 potassiums, 2 potassiums, 2 chlorines, 2 chlorines. So that's it right there. Okay. This is now balanced. This is our molecular formula. It shows my coefficients. It shows my molecules. And it shows the phase changes that it is in. It is completely balanced and put together. Right? So it shows coefficients, it shows molecules, and phase changes. You want coefficients. You want molecules. So like all of this is a molecule. All of these, right? But that's the one I'm using as an example. And it's going to use phase changes or phase symbols. And I forgot to write them down for this one. Let's go ahead and write those down. This is lead, always makes solids, and nitrates always dissolve in water. So the symbols are going to be like these, right? Solid, aqueous, whatever you have. Remember, lead is almost like 90% of the time going to make a solid. Right? So that's our molecular. Now let's go into the next one, which is going to be complete ionic. And as you guess it, it's just like we did on the back side, is where we dissociated our molecule and showed the ions. Right? So a complete ionic is going to be show the dissociation of the ions present. Shows dissociation of ions present. Okay. And in this one, we want to show the precipitate as a compound, and it's no longer going to be in its ionic form. So the precipitate is going to be a compound. I should write stays as a compound. Remember, a precipitate is a solid, and if you produce a solid, it's not going to ionize. Right? So let's go into our example here. Using the same one here, we want to dissociate it. Remember, solids don't dissociate, but everything that is in aqueous form will dissociate. Okay. So I'm going to have lead, because there's my lead nitrate. Now lead has a positive 2 charge. My nitrates right here, I'm gonna write those down. Okay, there is 2 nitrates. So I can write them like this, 2 nitrates with a negative 1 charge. These are both aqueous, so I'm gonna write AQ for aqueous. Okay, takes a lot of space. Plus my potassium chloride. I have 2 potassiums, so I'm going to write 2 potassiums. They have a +1 charge, and it's also aqueous. And I have 2 chlorines, and that is going to have a -1 charge for each one of those, and that's going to be aqueous. I'm running out of space, so I'm going to go ahead and do my product on the bottom, and I'm going to use a different color just so that we could tell it's the product and not the same one. So now I'm going to write these ones here. And for those ones, I'm going to be producing lead chloride. And we realize that it's a solid. So solid, it's not going to ionize. Precipitates stay as a compound. No S goes there. So I'm going to write my lead solid plus my 2 potassiums with that +1 charge, plus my 2 nitrates with their -1 charge, and both of these are aqueous. Okay? So this is this equation right here broken down into its ionic form. Now let's go into net ionic. So a net ionic equation is the other form that we're going to show it in, and it omits spectator ion. Omits spectator ions. And spectator ions are basically the ions that are just there to look. They're the looky looks, right? They are not doing anything to help in the creation of your precipitate. This right here is my precipitate. It is my PPT, okay? Precipitate, all right? So it omits the spectra ions, and spectator ions do not participate in the formation of the precipitate. So let's figure out what is part of my precipitate. Lead is part of my precipitate, and I have lead here, right? Chlorine is part of my precipitate, so I have chlorine there. Everything else that isn't there is going to get omitted. So I am going to have lead, Pb +2, aqueous. And this is not a solid, so it's not combined to this one. It dissociated, so it's separated. And quite honestly, I should just put pluses in between all of this because it's now all dissociated and broken apart. So I'm going to have lead plus chlorine, and there's 2 of those, and it's aqueous, producing lead chloride, and it's going to be a solid. Now, I don't know if some of you guys noticed, but I do have a typo here. I didn't balance my molecule correctly. If you guys notice here, lead has a +2 charge and chlorine has a -1 charge. So therefore, I'm going to need 2 chlorines for every 1 lead. Right? I actually wrote it over here, but I did not translate that over here. So I'm going to go ahead and put my number 2 right there. And this is a solid. Right? What is the oxidation state of lead chloride? That's solid? 0. Okay. All right, so now that I have these, this is my net ionic equation. Which ones were my spectator ions? Spectator ions do not participate in the formation of the solid. Or I shouldn't say solid because a precipitate could even be a liquid. So of the precipitate. also known as PPT. Okay, and in this case, my spectator ions were nitrate and chlorine. So it was 2NO3s aqueous plus my 2 potassiums aqueous, and those produce the same exact thing. If you guys notice, it produces the same exact thing. It repeats itself. So because it repeats itself, it kind of cancel out and they don't participate in that. Let's go ahead and do half reactions right here to make sure that we are correct. All right, so we have lead. This is the first one that we're going to do, the half reaction of lead. Should do this. Lead. Lead is going to go from a +2 to a 0. And chlorine is going to go from a -1. Actually, so let's write -1 to a 0. All right. It almost looks like, oh, they both went to 0. They both are the same. No. All right. In order to go from a +2 to a 0 in a number line, you actually have to gain electrons. You become more negative. And to go to a -1 to a 0, you're actually losing electrons. So you lost electrons. And you become more positive. And if you remember the saying, Leos do what? Leos grr. If you gain electrons, you are reduced. So lead has been reduced. And if you lost electrons, you are oxidized. So chlorine has been oxidized. You lose electrons, you're more positive. You gain electrons, you are more negative. All right, this is now officially the end of our chapter 6 notes. Chapter 14, you're going to see a lot more of these molecular, complete ionic, net ionic, half reactions, oxidation states, all that great stuff as we go through that chapter. But till now, feel free to practice your different types of chemical equations or classification. Remember, we have synthesis, which is combination, also known as marriage. We have decomposition, which is to break apart, also known as our divorce. Do not write marriage and divorce or homewrecker as answers because those are wrong. Those are only there to help you memorize what happens during the equation. So if it says, what kind of equation is this? And you're like, I can't remember. It's a marriage. It's going to be wrong, right? You have to remember the actual words, which is going to be synthesis or combination, decomposition, single replacement, double replacement, combustion, and neutralization reactions. This is how we take the reactions a little bit further. And if you guys notice, reactions in aqueous solutions, most of these reactions that occurred were double replacement reactions. Okay, they were double replacement reactions. Single replacement reactions, we're going to talk about those a little bit later when it comes to this on chapter 14. All right, my lovelies, take care and have a good one. Ciao.